Hello and welcome to my review of my Advent of Code 2024 in ARM assembly for the Game Boy Advance solutions. This seems to have turned into something of a series, doing assembly for Advent of Code, but that's alright. I'm going to start with my boilerplate code, so my template. Most of the functions, most of the code functionality that stayed the same through the days, although it did change a bit. I had to add in support for things like 16-digit numbers and changing the result output to give the CPU more time, more rendering time, or more computing time. But in general, it mostly stayed the same. Now, I kind of did a crash course on ARM assembly in the few weeks heading up to December, and so I'll show you first, okay, where I learned ARM assembly and for ARM assembly for the Game Boy Advance, and that was in this place here. Learn assembly programming with Chibi Aliens. It was very useful. It gave me a lot of templates to work from. Very easy to pick it up. And it did, like, ARM assembly has some interesting features. The way it deals with large numbers, with words, alignment, and addressing. Those sorts of things were tough to get your head around at times, but it did help out quite a bit, reading through some of the stuff. And yeah, so like I think I would recommend, if you're starting off with assembly, maybe give this side a try. He covers quite a few architectures, right, from Z80, 6502, 6800, or 68000, 8086, ARM, RISC-V, MIPS, and more, and more and more. You've got Super H in there if you want to learn for the Saturn, Sega Saturn, PowerPC. Right, covers a lot of architectures. So if you're looking for looking to get started in an assembly language, could be a good place to start from. So I used some of his examples as a springboard for my one. Let's have a look at my code. Let's get rid of that and let's have a look at it. So, all right. So this is how my thing started out. We start off ARM header, right? Tells the assembler that we're going to be using ARM. It's fine. Where to start off, right? Address 8000, 8. What is it? 8 million. Hex 8 million. Prog base, yeah. These sort of macro names: external RAM, internal RAM. In the GBA, you have, do I remember correctly how much it is? I think it's 24 kilobytes of internal fast RAM and 256 kilobytes of external, slightly slower RAM. The external RAM takes 6 clocks, and access time takes 6 clocks. The internal RAM, I think, is just 1 clock. Might be 2 clocks, but it's, faster to access it. I think I had to use the external RAM twice. May have just been once. We'll get there. We'll see. We'll have a look. Monitor width, I'm not sure. I think that probably gets used later down. That came in on the examples. That's all right. Set up the starting point, GBase start, right? Just a branch, right? Just branches down to here. Starts it. These are DMA addresses. I think I actually don't need those. I think I got rid of all the DMA stuff, so those could probably be deleted. Oh well, that's right. Anyway, resx. That's where my result sprites start getting printed for the x location. Right, xy coordinate, x coordinate. Result 1y and result 2y, those are the y coordinates for the result 1 and result 2, where they start from. Res 1, res 2, p. These are the palette. Seeing the palettes for result 1 and result 2. So remember, I use white for result 1 and red for green for result 2. These ones here set the addresses, the memory addresses where result 1 in the binary and the result 1 in decimal, result 2 binary, result 2 decimal appear in memory. They will stay in the internal RAM. We load in the GBA header. Now, GBA header, we have to have this to have the GBA load a ROM, you have to have a Nintendo logo header. This is different from the logo that Chibi Aliens had in his example. It may have worked in the emulator that he had, but it wouldn't work with my card. I had to use a patch. I had to patch it, and then I copied the result from that patch and put it into my my header file, so I didn't have to patch my ROM every time. And then all the rest I basically left the same as what was on there. And then ASM.NET, I mean, I should have changed game titles and all that stuff. Doesn't matter. But that's just all the header information that has to be there for the game to load properly. So we start out, set up the stack pointer, that address. We've got this setting up the LCD, the screen, right? So what are we doing? We're setting. See, unfortunately, we've got this one here on 400 instead of using binary to set it out. I believe we set it up as BG1. I think it was BG1. And that's it. BG1. I'd have to check again what BG1 was. I think there's like 2 background. Or BG0, sorry. BG0. 2 background screens. And then we set up again. And this is where you get a little weird thing that tends to come up in ARM, is that there are certain addresses you can't directly move into, like immediate. There are certain immediate values you can't move into registers. They have to follow certain patterns in order to get them in there. So if you want to load something that's into a register that doesn't follow that pattern, you first load one that does follow the pattern, and then load a second one that follows the pattern, and like add or logical OR in the remainder of that value following the pattern to get it in to the register. And that's what's going on here, where you can't just use hex 04000008 directly into the register And so you have this, like, yeah, set up like that. It's weird. ARM is kind of weird in that way. And yeah. So again, so we chose GB0, BG0, and now we're setting up the screen for BG0. Priority, character base block, and screen size. I think there's another one that we're setting in there. That's what we want. I mean, it sort of sets you over here, doesn't it? Pattern base address, right? And then the screen size. 64 by 32 tile map. And so that gets you 2 screens. This is something that I set up, actually this part here, which is setting up the vertical blank interrupt. And that's how I later on called the refresh the result output. So we have here, we have these further down here, these addresses, the interrupt pointer and the interrupt handler. We'll go over those a little bit later. So we give the RSR pointer the address of the RSR handler, the interrupt handler, right? And then these ones here, I'm setting up on the LCD for the LCD the interrupt on the V blank, and setting up for the system turning on the interrupt for the V blank as well. That's all setting that up, configuring it for on the V blank. What I was doing, what I was doing to begin with was, firstly, what I was doing at the very beginning was that I wanted to, every V blank I was updating the results. And what I actually do further down later on is that I convert it so that when I update the results in memory, I enable the interrupt, the V blank interrupt. And the V blank interrupt, after updating the results for the screen, right, sending the new sprite updates to the screen for the display, it disables itself, right? So if the results, haven't been updated since the last frame, since the last V blank, it doesn't interrupt to process that, because the conversion from binary into decimal for the display is quite heavy, quite slow. So that saved that saved a considerable amount of time later on, setting it up like this. But we'll get back to that later. Okay, so we get into the next part. Here we are loading our palettes, our character tiles, the tile map, and tile map 2. These are our backgrounds, sprites, sprite character tiles, right? Loading all of those into a memory places. Right. Loading these all into memory. See here we've got screen 1 and screen 2. So I can have a look at that now. What was the background? Here we are. So we've got this here, which is showing our background styles. You can see up the top here, I actually have day 1 listed up there, right? And what we have over here is day 1. Subtract hex 10 from the values, and you get what they are. We D A Y 0 1, right? And then you have silver and gold down there, and then we have a second screen, which at the bottom has this part here, which says done. So once it finishes the result, prints the result, it will change to saying done. So effectively, actually I'll show it so I don't have to so you can visually see it. Let's see, I need this one here, don't I? Oh no, it's not showing. Wait a second. Let's load another one just to make sure I've got this right. There we are. Now I have to capture something. There's my window capture. I'm not. Bonk, there we go. Alright, so we have the first screen and the second screen over here. When the result, when finished parsing or finished handling the input, you're finished computing the results, the screen scrolls to the right, and you see the done message, and then if you start it again, it scrolls back to the beginning. It scrolls back to the left. So that's how I show completion later on in the days, in the days, yeah. Alright. Apparently I don't have that set up on the first one. That's right. Of course I don't have it set up on the first one. Because I didn't go back and actually update those. Anyway, that's fine. Right, so the done message. We have all the palettes. All the stupid palettes. Set up in here. Apparently there's some tabs here that should be spaces. I think I moved those around. Right, got the palettes and the background maps. Right, so we load all those in. There's also we've got this char tiles end and char tiles. That's going to point down to, where are we? Here. Right. This bit here, which is the char tiles bin, right? Which is my font, effectively. That's right. Okay, so we've loaded all the tiles, we've loaded all the backgrounds, load the palettes. Good. First thing, we branch into clear results. Okay. Right. So what to do in clear results? So we have this command here, which handily in one command backs up all the registers, or all the listed registers, to the stack in one go, which is great. Then we move zeros into 0 and 3. We load the result addresses. They have pointers to somewhere else. We store 0 into, and we're storing these as words, right? 4-byte words, 32 bits, into the addresses, and then with the offset of 0, and then we add 4 to the offset, and we store them there. Right, this is especially required later on where I'm dealing with 64-bit numbers, so I need two 32-bit words I need to wipe. And then we have a single command which will clear which will load from the stack in one go, all those values. Very useful. Alright, so we've cleared the results. Now we have to clear the decimal. Right. So branch to clear decimal, and now we have to clear out the decimal portion of the result. Right, because that's where the screen always updates from. So we need to wipe that out. So same sort of thing, we load 15 in here because now I've got 16 digits. I think it's 16. Yep, 16. 0, we've got these, we load these two pointers, the two registers to the two decimal addresses in R1, R2. Offset of 16, and now we're storing byte, strb, store byte. Of register R0 into R1 with the offset of R6, right? Offset of 16. We subtract 1, and this is one of the fun things of ARM. Oops, I deleted something. This S. A lot of instructions you can put an S on the end, and it will set flags, set status flags, right? So if I did that subtract and I didn't use the S, say, and it reached a 0, if I didn't have the S, it wouldn't set the 0 flag. Right? You'd have to do a compare R6 to 0 to see if it's 0. But I have a choice here. I have the choice of setting the flag when I do a subtraction or a addition or anything, like anything really. When you do a logical rotate or shift left, shift right, you can set the flag. You can use an S to set the flag. And so that's how you get things into the status flags, the overflow or the carries. You can do it like that. So when I do the subtract, I set the flag, I check if it's positive, right? And if it's still positive, then we go back to clear loop. So when it's 0, it'll still be positive, but then when it subtracts one more, it'll go to negative, and we'll exit out. So that way it goes from the offset of 0 up to the offset of 15. So 16 values. Alright, so we go back. In the next one, I have the branch to enable interrupt. I enable the interrupt at the very beginning because we want to have the basic interrupt. Here we are. We want to have the zeros, effectively, the initial state showing up on the display when it starts up, right? So this one here, I'm only backing up R0 and R1, right? So we start up this one here. This one here, I can load 04 000004 into R0 immediately, because 04 and 04 match, and this 00 and this 00 match, right? So that's a valid number you can put into a register in one move. ARM is weird, right? And then we move 08 into that that memory address, which enables the interrupt, the v blank interrupt, and then we quit out. All right. So I almost feel like we should have a look at the interrupt handler while we're here. Let's do it. Let's do that. So here's our interrupt handler as well. Back up a lot of registers. I probably don't need to do this many registers in here. That's all right. So we come in here. We we've received an interrupt. So we want to load this here and check which interrupt it is. If it's not number 1, which is the v blank interrupt, if it's not that, then we just exit. Oops. There we go. Then we just exit. If it is the number 1, then we call update. I'm just going to update the screen. Then we move 1 into that store 01, the half byte, 16-bit, into that address, which will clear the interrupt. And then we also store 0 back into this address here, same one as below, which will disable the interrupt. Right? So basically this will go through a pattern of enabling the interrupt whenever I've updated the result, and the interrupt then updating the screen output and then disabling itself. Alright. So we've done the enable interrupt, exit interrupt, interrupt handler. Let's go back. Call update. We'll get to call update in a bit. Then we come into this loop, this forever loop, right? Where we read the button, we clear the results. So push the button, we clear the results, right? Which might have to be done if I'm running it twice. What would I do here? This scrolls the screen to the left, right? So if it was scrolled to the right saying done, it'll move the screen back to the left side where the done message is not visible anymore. Then it'll branch to solve day, and then once we come back from solve day, it'll scroll the screen to the right, so you'll see the done message, and then we go back into this loop, which sits here in the read button. So let's look at read button. That's the next part, really. Let's probably have a look at call update. We'll look at call update in a second. Here I'll go over this a bit. We've got a whole lot of labels here pointing to addresses or values. This is another thing in ARM. A lot of the time, if you want to reference values or addresses by labels, you have to have a label within a certain number of bytes from where it's being referenced, and so sort of spread through the code, in my case at least. So spread through the code in some semi-random places. I've got these labels with values or memory addresses placed so that they can be referenced. And they're usually set around these align 4s just in case I've put like a byte or a word. You then have to align the next values with 4 bytes, because that's the way that ARM works as well. It needs to be like everything sort of needs to be aligned with 4 bytes. Alright, so we've got read button. Here's our loop, which is waiting for the button to be pressed. We've got R1 gets a 1 put into it, and we'll wait. Deleting lines. We're waiting for the button to be released. Okay, so we're loading the values for the buttons, the joypads, we AND them, we load it in, we AND it with 1, right? We check, compare it to 0. If it's 0, then the button is being pressed, and we set R1 to 0, right? If it's not 0 and R1 is 1, then we want to stay in here. We stay in the loop anyway. So R1 has to be 0, R2 has to be 1 to exit this loop. Okay, so we come in here, right? R1 starts off as 1, so we're going to be stuck in the loop. Once R0 becomes 0. Wait a second. I don't know. It works. It works. If R2 is 0, it will always keep branching to set flag, right? So while you're holding the button down, it will keep taking this branch to set flag. But as soon as you release it, then it won't take this branch, and R1 won't be 1 anymore, and so then you'll exit button and it will continue on, clear the results, and do solve day. Alright, and then we've got this one. Oh no, the next one, call update. But call update is 2 parts. For some reason I clear the decimal here. Don't ask me why. It's just in here. Maybe I should have clear decimal. I should have clear results in call update. I don't know. I guess whatever. No, wait. No, I know why. I know why I don't have it in here. Because when I'm updating the results, I need to clear the decimal in case the value's sort of gone down, or a higher portion of the value changes and not a lower portion. I need to make sure that the decimal value is updated every time call update goes. So we clear that out first. I keep deleting things. We clear the decimal results, and then we load in. We prepare the addresses for result 1 binary and result 1 decimal, which is what result 1 address and result 1 dec address stand for. Then we branch into dubdab, and then we do exactly the same thing with result 2. So we'll cover it once. So dubdab, this is my implementation of a double dabble. Let's check that, shall we? I'll bring the browser back for a second. Yeah, I know we can't see everything. Oh, that's fine. Let's see. How much are we missing? I can go like this, actually. I can... I can change the crop from the right. Do that. Yonk. There we are. Basically see everything now. Almost. So, double dabble is a way to convert binary numbers into a binary encoded decimal notation. I do it slightly different. What they've got in here, where they use nibbles to represent each binary, each decimal value, right? So 4 bits for each decimal value. Whereas in my case, I'm using a whole byte for each decimal value. But that's okay. It's fine. It doesn't add that much to the computation. It doesn't add that much to the complexity of it. So what am I doing here? And I also have to do it with 64 bits. So that's a bit of a pain. Right, so set up some values, some starting values. 7 is an offset, I think. 3 is another offset. Move R1 with 0. So I load R0 with from R9. R9 was the binary version. Yep. Right, R9 was the binary. R8 is the decimal. And we compare it to see if it's 0. So we have to start with start with the high one, right? I start with the high address. The high bits. Am I doing something? Odd here. I think I am doing something odd here. That's alright. We start with the high bits. The high word of the 64, the high 32 bits of the 64-bit number. Right. If it's 0, then we skip high. We go down to the next part there. Right. Otherwise, we load each byte. And what I want to do first is that because ARM is Little Indian encoded, where the first byte going from left to right, the first byte is the lowest byte, then the next byte is the next highest byte, then the next byte is the next and next, so on. I want to reverse that. I need to reverse it so it's basically big Indian. So that's what I'm doing here. I load each byte. I shift it left. I shift one left by 8. And I add it on, and then I add the value that I loaded here on. And I subtract 1 from. That's right. So that's why I'm using 13. Yeah. Okay. Yeah. That's why I'm using That's why I'm using 7 here. It's a bit weird. So using 7 here as the offset, and I don't load, and I'm loading the full word here. What happens with ARM is that if you do a load that is not aligned, it rotates around the position you're loading from, which is it causes all sorts of problems. Anyway. So I basically reverse the order of the bytes in the word here, and then we go into push bits. Yeah. And so I need R2 to be 3 here because I need this for the comparison. I can't use branch positive or not equal because it needs to stop on 3. That's alright. So then we go into push bits, branch into push bits. Right, we're going to be pushing 32 bits, so I set R4 to 31. I move what's in R14 into R11 for some reason. Don't ask me why. What was R14 again? So I'm moving that back out at the end of this. Oops. Undo. This is the program counter. There's a program counter. or it's the return address. It might be the return address. The LR, the value in LR, I think. R14. Can you see it on screen? We can. That's good, because I still got the browser on there. Let's get rid of the browser. Because I'm branching here and I'm not doing this sort of store, I have to back up the value that's in that return address, so that I can actually return back up here once I'm done in this loop, because I'm going to branch out somewhere else. So I'm coming here, we move. This is, again, I'm using the S here to push it onto the whatever value gets shifted left, LSL, logical shift left. Moving that onto the carry flag. We move R6, put R6 into 0, and then I add with carry that R6 with 0. So if there was a 1 in that got pushed into the carry flag, R6 will be 1. There is a 0, then it's a 0, it stays a 0. Then we branch the dub-dab roll. Come back in the dub-dab roll here, and now I've got to do 15 because there's 15 digits, right? So go through this loop 15 times. We load the byte that's in the first position of the, I'm using R6 here, so which is, remember, points to res1 decimal address. We AND, keep deleting things. We AND the value of R1 with F3 OF, and we store it into R3. We compare that to 5. I don't think I actually, well, I don't think I actually need to do this. I should just be able to compare what's in R1. Anyway, we add, if it's, and this is another one, right? Another thing which we really have in ARM assembly is that these comparators we can use on basically anything. Right? When it was in 6502, the comparatives were mostly used on branches. So you compare, and then you branch not equal, branch positive, branch equal, right? In ARM, we can put those comparative values on basically anything. So this one here, I'm doing add greater or equal. Greater than or equal to. So if R3 is greater than or equal to 5, we add 3 to it. Right? Then we shift it left by 1, and we add in the value of R6. And then we move. We put 0 into R6, deleting things again. We put 0 into R6, and when we test R2 to see if hexadecimal 10, so if it has pushed past the first nibble, right? If we've reached the 5th bit, it's become a 1. If it has, well, if it's not equal, then we AND. We do an AND with R2, R2, with F. We AND it with F. And it's also not equal, then we add. We push 1 into R6. And then we store that byte back into our list, the binary list, and we subtract 1 from the subtract 1 from thing there. Now I'm a little bit worried about this not equals. I think in this case, when you do test and it comes up equal is the same as, okay, yeah. I think, was it test is effectively the same as doing an and? And so, in this case, the result would be not a 0, right? If you and with 0 with hexadecimal 10 and the 5th bit is set, then the result you get out would be hexadecimal 10, and so it's not 0. So yeah, if it's not equal, then we set those values, like we effectively trim R2 down, so it's only the 4 bits, and we put 1 into R6, so that the next time we go through this loop, right, loading the next character, we'll be able to add that carryover, that overflow from the first nibble into the next place. And I'll do this for all 18 bytes, effectively moving it along, right? And it has to do this each bit. So for each of the 32 bits, it has to run this 15 times, do this loop 15 times. So it gets quite time consuming, right? And that's only the 32 bits. If we had the high byte, if we have the high byte in there as well, it has to do it 64 times for 16 times. It has to go through that loop. So once it's done it 16 times, it comes out. It subtracts 1 from this 31 and goes back through it. And once we get to the end, we restore that return address. We jump back, right, to push bits, and then we'll do the low part if we're having to do the low part, and then we exit the dub-dab back, right. So we've done the dub-dabs, deleting things again. Done the dub-dabs, and then we branch into update output. So update output, this is a lot of the copy paste code again. I made changes though, like some of this R6 and R5, R6 15, right, we've got the 16 places, the 16 sprites per line. R5, I'll figure out what that is later. Right, work out which sprite number it is. So we come in with this. R9 is the address. We're pushing that into R1. For some reason, that's the result address. The binary. Interesting. Multiplying. So this is working out the x coordinate. Right. So we'll start off with the rightmost digit. We multiply 6 by. Where is my 5? R5. It's up here somewhere, isn't it? Must come somewhere else. Oh no, I got 5 is that one up there. 8. Right. So this is 8 is the width of a sprite. Right. A sprite is 8 pixels wide. So we're multiplying 6. In this case, 15 by 8. And we're storing that in R2. Then we add the x coordinate to that. So we're making that offset of how far across to put this the sprite that we're loading. We load in the sprite, load in the value, which is going to be 0 to 9, the decimal value in that location. We add 10 to it because the locations of the sprite in our character, my character table, my font table, has a 10 in front of it. For extra characters, extra ASCII characters, we're moving what's in R10 into R3, which is our R10 is our, don't know why. Should just have it put into R3 anyway, whatever. Into the palette. We add whatever's in R4, which is the tile number. Alright, we see our color palette layout thing here. 4 bits are the color palette, 2 bits for the priority, and then like 10 bits for the palette, the tile number. Right, so the palette. So like we set up the tile number here. We put the palette. Yeah, we set the palette here, and then we add the tile number to the palette, and then we branch to set sprite, and then we add 1 to R0, which is the sprite number. So sprite number, I do start off as 0 up here, so that's alright. And because, see, I don't back up, I don't store R0 here because the sprite numbers have to not overwrite. So updating the sprites, I'm going to be updating 32 sprites. And so I have to start at 0 and go all the way up to 31. If I don't do that, if I overwrite the values, then it'll overwrite the sprites. So I don't back up R1, R0, I just keep it all the way through. Add 1 to it, subtract 1 from R6 here, and we loop it. And then we've got set sprite. Where is set sprite? Here we are, down here, set sprite. So this actually writes the sprite out to the memory OAM, sprite OAM. Those values that I set up, like R4, R0, R3, R2, they're all used here. R4 is not used, that's right. So we load in R4 that address for the sprite, for sprite OAM. We add the sprite number to it, and we logically shift left 3 for some reason. This is 8 bytes per sprite used. This could be a one of those loading ARM addresses things that goes on. Anyway, then we store in that address R1, which was the of these values, like the shape of the sprite, colors, rotation, the Y position, into R4. We add another 2 to R4, that address, that memory address. Then we store in the X position and those horizontal vertical flips, rotation values, and another 2. And then we then we store in the color palette and tile number finally into R4. and then we exit back out, go back out. So that's setting the sprites. Alright, so that covers the updates, calling updates, update output, and send my output to the screen. Okay, so we're almost there. We've gone through this. There's one thing here which is another thing that copied out this part here. The LDIR 16 and B. Now this is how you transfer sprite data, palette information, and that into the memory. And this is something I just copied from that Chibi Aliens guide. So he can explain it. I don't have to know this. All right, so we finished all that. We've finished our interrupt things, and somehow I've ended up back here. Why? Was it no H? Wrong things. There we go. Set the sprites. Done the double dabble, and now finally, this is the part that we'll see most in the coming episodes. The solve day section. Right. So I start off the solve day section. I've got this these addresses for the result 1, result 2 address, and another address that's in here called shuffle buffer, just pointing to somewhere in RAM, and it will get changed in many different days. We solve day, backing up the registers to the stack, deleting lines again. I load 2 registers with the input address and the end of the input. Very useful for working out if I've reached the end of it. I can't remember if I actually use this. Right. And then my loop for start off our loop for reading through the input. And when I finish the day, we go back where we came from. And then down here we have our input. And my input right on the end. Yeah. So if you are going to build this for yourselves to test out, you want to have your input file, a text file in the directory called something like input 1, input 2, input 3, and so on. Okay, and in the end, I think I actually showed it before, but in the end it looks sort of like this on the screen. Only I don't have 15 digits or 16 digits on this one, day 1. That'll come later on. Alright, so that is the introduction done, and I've spent like an hour on that already. So I hope I will see you again for the day 1 explanation review. We'll see you then.